Welcome everyone, I am Moreno Quatra and I am a PhD candidate at Politecnico di Torino. In this video, I will briefly present you the paper entitled How much attention should we pay to mosquitoes co-authored with Lorenzo Vaiani, Alkis Koudounas, Luca Cagliero, Paolo Garza and Elena Baralis. This paper presents our approach to the mosquito detection task at ComParE 2022 Grand Challenge. First of all, I want to start with the motivation behind the task itself. It entails the detection of specific audio events, and in this case, the task aims at identifying the presence of mosquitoes in raw audio recordings. The goal is to identify the timestamps related to the beginning and the end of the mosquito in the audio sample. As you can see in the image, the system is presented with an audio recording, and some regions could contain the signal corresponding to a mosquito. The presented model should be able to detect those regions and separate between audio frames containing mosquito events and portions containing only environmental or background noise. To detect those specific parts, the model should be able to identify the starting and ending points of the mosquito inside the entire waveform. However, such kind of data samples are very hard to obtain. Indeed, the task organizers proposed the use of an uncommon data collection consisting of human annotated audio recordings. Each audio sample is annotated at sample level with a class indicating whether it contains mosquito events or not. Frame level annotations are unfortunately not available, both because such samples may be very difficult to obtain and expensive to annotate. In these settings, we identified two main challenges. First of all, we deemed as crucial the use of contextual information to identify the exact starting and ending points of the audio event in the raw audio sample. Indeed, designing a model that can leverage contextual information can help boosting the overall accuracy. On top of that, the second challenge was related to the availability of data with frame level annotations. Having separate recordings, each of which has a single class annotated at sample level, it is not possible to train a contextual frame level model, therefore requiring the use of sample level models. To address the first challenge, we propose the use of an attention-based architecture for the analysis of raw audio samples. Transformer-based models are currently dominating the field of natural language processing, and the attention mechanism has been shown to be effective in many settings. Even in the field of audio processing, attention-based models were recently proposed and shown to be effective for addressing various tasks such as automatic speech recognition or speaker diarization. In some ways, the proposed task is similar to the problem of speaker diarization, as it deals with the detection of sound events within an audio recording, and in particular with their starting and end times. So the proposed model leverages a CNN for feature encoding that produces audio tokens, and a transformer architecture that processes the sequence of audio tokens using the self-attention mechanism. While the use of contextual information could be reached by using the proposed architecture, we still miss data samples that can be used to train such models. To address this specific challenge, we propose a data augmentation technique to artificially generate training examples for the audio frame classification task. Specifically, what we propose is the composition of audio samples containing background noise and other containing mosquito events. For example, given an audio recording with environmental noise and another one containing the mosquito, we randomly select a starting point and sum up the signal containing the mosquito at a given starting position. Given that we know both the starting point and the duration of the audio sample containing the mosquito, we could generate frame-level annotations for the augmented audio sample. In the example here, it is possible to see the process in action. At the bottom, you find an example of the sequence tags, where the O class corresponds to the background and the label M is associated to the presence of the mosquito. Although this could be enough for training the audio frame classification model, we also propose different labeling schemes. Okay, so given the information obtained with the data augmentation technique, we propose the two-label classification scheme that is the most straightforward approach. In this case, the label O is assigned to frames that contain background signals, while all the frames containing mosquito events are labeled with the class I that stands for internal. The three-label scheme introduces an explicit class for marking the beginning of the mosquito event. The frames containing mosquito are assigned to the class B if they are at the beginning of the event, I otherwise. Finally, in the four-label scheme, we follow the same principle of the previous case, but we also explicitly model the end of the event with the label E. So at the end, there are four different classes for the classification task. For our experiments, we used Wav-MoDe 2.0 as base model. It is a transformer-based architecture pre-trained using self-supervised learning, and it imposes a fixed length for each frame that in this case is said to be 20 milliseconds. For model training and evaluation, we use the HumBugDB dataset provided by challenge organizers. It contains almost 35 hours of audio recordings with a roughly balanced split between mosquito and noise recordings. It is divided into three subsets. The training set is used for training the model, while two separate evaluation splits are used for selecting the best checkpoints. Finally, the organizers provide a blind test set that is used for final model evaluation. During model training, we set the maximum length of the input audio sample to 60 seconds, while during inference, we experimented with different attention windows ranging from 60 milliseconds to 60 seconds. The challenge has an official evaluation metric that is the polyphonic sound detection score. It is designed for sound event detection, and it is a perfect fit for the challenge. Additionally, we evaluate the model using the detection error rate that is defined as the ratio between the sum of false alarms and missed detections divided by the total number of frames. This metric is often used for evaluating speech activity detection, and given the similarity with the proposed task, we also use it in our evaluation. In this slide, you can find the table summarizing all the results of the proposed model. First, having different attention windows, we can see that the model performances increase while decreasing the attention window up to 600 milliseconds, with the model using 60 milliseconds, so the lowest attention window, being the worst among all others. Those results demonstrate that the contextual information can be useful for frame classification. Indeed, the 60 milliseconds window gives the worst results, but too much context can decrease model performance, giving noisy and unnecessary information to the model. Analyzing instead different labeling schemes, we can see that the best results are obtained using the four-label classification scheme that explicitly models starting and ending points of the sound event with specific classes. In the table, you can see that there are two different columns for the PSDS score on the test set. We will discuss it in the next slides. Finally, the best model is obtained by setting the context window to 600 milliseconds, corresponding to 30 frames, and using the four-label classification scheme. From the previous table, we can see that the model is able to reach good results and can beat the proposed baseline. However, thanks to the challenge organizers, a qualitative evaluation shows that the model tends to generate wrong predictions containing short-lasting background intervals with long-lasting mosquito events. The default setting for the PSDS metric seems to overlook this behavior, assigning high scores to our model. However, by changing the parameter controlling the maximum false positive rate, the obtained results are significantly worse with respect to the default settings. For sure, this behavior will require more attention in future works. Okay, so we can wrap up this presentation with some takeaway messages. First, we present a transformer-based approach named Wav-MoDe for identifying mosquito events in raw audio recordings. The attention seems to be helpful to identify the mosquito events in the raw audio signal, but very large context windows may introduce unnecessary context that can degrade model performance. Finally, the proposed evaluation metrics tend to overlook some errors that can be found in model predictions, and this could affect the relevance of the model in real-world scenarios. So we have several plans for future works. First, the proposed model is based on Wav-2Vec 2.0 that relies on signal tokenization and quantization. And while this could be helpful for tasks such as automatic speech recognition, it could limit model performance for the proposed task. Second, the proposed model is designed for offline analysis of recordings and relies on signal splitting for long audio recordings. We plan to investigate the design of a streaming architecture that can analyze a continuous audio stream without the need of splitting the audio signal into smaller chunks. Finally, as reported in the previous slide, we want to investigate the use of other evaluation metrics that can give a better overview of model performance in different settings. Okay, so here you have the references for this presentation. Please be sure to take a look at our paper if you're interested in a more comprehensive description of the methodology and a full list of references. And that's all for this video. Thank you for your attention. I look forward to interesting discussions at ACM Multimedia 2022. Thank you.